In this exercise, we are going to derive the formulas for the Möbius transformations or linear fractional transformations for two different cases. The first Möbius transformation that we will look for is supposed to map three distinct complex numbers z1, z2, and z3 onto three distinct points w1, w2, and w3 of the extended complex plane. For case 1, w3 is the point at infinity. For the second Möbius transformation, z3 this time is the point at infinity, while w3 is a finite complex number. Let f be the Möbius transformation, so that f of z equals the quantity az plus b divided by the quantity cz plus d, with the discriminant ad minus bc not equal to 0. For the exercise, we have f of z sub 1 equals w sub 1, f of z sub 2 equals w sub 2, and f of z sub 3 equals w sub 3. Let's get started with case 1. If f of z sub 3 is infinity, the denominator c times z sub 3 plus d has to be 0, or that d must be equal to minus c times z sub 3. If c were to equal 0, then d would also be 0, and this would make the discriminant ad minus bc equal 0. And so c cannot be 0. We divide every term in f of z by c. And let a sub 1 be equal to a over c, and let b sub 1 be equal to b over c. D over c, of course, is minus z sub 3. And so f of z equals a sub 1 times z plus b sub 1, divided by z minus z sub 3. F of z sub 1 equals w sub 1 implies that the quantity a sub 1 times z sub 1 plus b sub 1 divided by the quantity z sub 1 minus z sub 3 equals w sub 1. F of z sub 2 being equal to w sub 2 implies that the quantity a sub 1 times z sub 2 plus b sub 1 divided by the quantity z sub 2 minus z sub 3 equals w sub 2. We solve these two equations simultaneously for a sub 1 and b sub 1. A sub 1 equals this fraction, and b sub 1 equals this other fraction. The discriminant is a sub 1 times minus z sub 3 minus b sub 1 times 1. This factors out nicely into the product of the following quantities: w sub 1 minus w sub 2, z sub 1 minus z sub 3, z sub 2 minus z sub 3, and everything divided by the quantity z sub 1 minus z sub 2. Every factor in this fraction is non-zero since the z sub i's are finite and distinct, as are w sub 1 and w sub 2. W sub 3 is the only one that is infinite. Therefore, the discriminant is non-zero, so that we have the formulation for the Möbius transformation f with a sub 1 and b sub 1 given by these fractions. In case 2, z sub 3 is the point at infinity, and w sub 3 is finite. If c is 0, then AD must be non-zero, so that both A and D are non-zero. But this would mean that f of z, which is the quantity az plus b divided by d, would tend to infinity if z were to tend to infinity, and f of infinity would be infinity, and not the finite value w sub 3, so that c cannot be 0. We divide all the terms in f of z by z. If z were to tend to infinity, f of z would tend to a over c. Therefore, if c is not equal to 0, W sub 3 has to equal A over C, since f of infinity is W sub 3. We divide all the terms in f of z, this time by c. Let b sub 1 equal b over c, and let d sub 1 equal d over c. And so f of z equals the quantity W sub 3 times z plus b sub 1 divided by the quantity z plus d sub 1. F of z sub 1 equals the quantity W sub 3 times z sub 1 plus b sub 1 divided by the quantity z sub 1 plus d sub 1, and this should equal W sub 1. F of z sub 2 equals the quantity W sub 3 times z sub 2 plus b sub 1 divided by the quantity z sub 2 plus d sub 1, and this should equal W sub 2. We solve these equations simultaneously for b sub 1 and d sub 1. B sub 1 equals this fraction, and d sub 1 equals this other fraction. The discriminant is W sub 3 times d sub 1 minus b sub 1 times 1. The discriminant is equal to the product of the quantities W sub 1 minus W sub 3, W sub 2 minus W sub 3, and Z sub 1 minus Z sub 2. We divide this product by W sub 1 minus W sub 2. All the factors in this fraction are finite and non-zero. Since the W sub i's are finite and distinct, as are Z sub 1 and Z sub 2. And so the discriminant is not zero, so that f of z, with these values of b sub 1 and d sub 1, is the Möbius transformation for case 2 when W sub 3 is finite and non-zero.